But our hope is that with machine learning, we can better acquire this contextual information, as well as we can better utilize this contextual information. So I will talk a little bit about that. I want to acknowledge a few people who helped me put together the presentation, as well as our university collaboration, which I actually have used to develop this presentation. So before I actually talk about this topic, I wanted to also give a little bit, very briefly, a broader view of AI at Intel. So Intel actually has a whole product division, which is developing products for AI. So not only hardware, general purpose hardware, but also custom built hardware for optimizing deep learning solutions, and the entire software tool chains on how a developer will use, develop deep learning methods to work on this hardware. And they also work a lot with ecosystem partners across different industries to develop end-to-end solutions. There is a fair amount of effort on AI research at Intel, and in the labs, actually, we are focused on improving the computation for machine learning. And we are not only developing algorithms, software, and hardware for improving deep learning workloads, but also looking ahead to newer architectures such as neuromorphic computing, which is brain-inspired computing, which allows you continuous learning, as well as trying to apply quantum computing type of ideas to machine learning. And there are various research initiatives ranging from heterogeneous computing, where FPGA acceleration is used to improve the performance of general purpose CPUs for learning, as well as probabilistic computing, which is an idea of how do you actually compute with probabilities, which is relevant for machine learning. And then also developing silicon for some of these newer architectures, such as neuromorphic computing and quantum computing. And I just wanted to point out that Intel actually has done a new chip, a test chip called Loihi, where it uses this new architecture, neuromorphic architecture based on spiky neural network to develop very low power machine learning solutions. And they have a very active effort to engage with academic partners to develop solutions for this particular chip. So today we are not going to talk about that, but maybe this is a future presentation that we can work on. So in terms of what we are doing in wireless, I think like everybody in the industry and academia, we are also trying to comprehend how best to utilize wireless, machine learning for wireless applications. And if you look at, start reviewing the literature from the past couple of years, there's a surge in various applications, and actually Tim's talk was very exhaustive in listing out what can be, how machine learning can be applied. I tried to capture this few examples, which could be of interest. So I think at UT, Robert is doing a lot of work in applying machine learning to improve millimeter wave communication for vehicular networks, which is a challenging problem because of high mobility and density of vehicular devices. So the idea is that you're going to use contextual information such as positions of these vehicles to better do beam management. So I automatically predict which beam to use based on this location information. So this is a kind of optimizing a physical layer problem. There is also work to look at the MAC layer and try to develop radio resource management solutions to improve the connectivity, vehicle-to-vehicle connectivity, as well as vehicle-to-infrastructure connectivity using reinforcement learning techniques, and this is work done at Georgia Tech. And I think Tim just talked about how you can develop autoencoder solutions for end-to-end, developing new solutions for end-to-end communication system design. Also, there is work at applying machine learning at the application layer. Professor Goldsmith just actually talked about how you can apply machine learning for context-aware source and channel coding. And some of the key ideas in her talk was that if I'm transmitting certain text over wireless networks, I'm going to capture the semantics of that text using machine learning, and I will use that information to basically, if I can preserve the semantic information to deliver to the device, then I really don't need to produce the text exactly. So these are some examples. If you note that they do utilize contextual information to improve the performance of wireless systems. And the second thing to note is a lot of them are looking at more complex applications such as the supporting autonomous systems on wireless networks. So these are, while we are interested in a breadth of machine learning applications, we have done some work in exploiting contextual information as well as looking at the problems of applying machine learning to wireless autonomous systems. So I'm going to talk a little bit about that in this talk. So actually, just like Robert applied position information or location information to the problem of beam management in vehicular networks, we've looked at using location to do cell selection and beam prediction in aerial networks. And I will cover this in a little bit of detail. So, I mean, the main idea is simple. If I'm a user, my location actually does depend on which cell I'm going to connect to, or more generally, if I'm using directional communication, which beam I'll use for transmission. So you can then exploit this correlation to automatically then, based on my location, just automatically select what my best cell or best beam is, and that will save me a lot in scanning and searching across multiple cells and so forth. I'll reduce overhead, latency, and power. So to do that, I need to develop a map of, if I'm at this location, what is my best cell, and kind of do it more generally across its spatial environment. And we've worked with Harvard University on this. So the idea is to really employ a tool from computer vision, which is known as conditional random fields, to develop this map. And the idea between conditional random fields is, actually there is some slides in the backup. I'm not going to go into the detail of the math, but really if you have basically some observations which are, let's say if you look at the three-dimensional grid where we want to develop this map, you know the actual value or the true label at very few locations, which are the yellow positions on this grid. And what you want to do is infer what the best cell, best beam would be on the red locations. So you treat this problem as, like at every node, the best cell is a random variable, and these random variables are jointly distributed according to some probability distribution. And you make an assumption on that probability distribution, but these distributions have certain parameterizations that you're trying to learn. And based on kind of this known labels, you try to infer the parameters and solve for this problem. And once you have the distribution, you look at the marginal and you figure out, okay, what's the best probability, what's the maximum, you select the cell with best probability. So that's basically the idea. And we have applied this to the problem of cell prediction in aerial communication. So drones flying over a cellular network, how can they automatically select their cell? So the idea is, it seems like this would be a good problem to apply machine learning to, because the aerial environment is less cluttered than a terrestrial environment, and it will be relatively stationary and easier to predict. So we want to test that hypothesis. There is, of course, even though it seems very predictable, there are some challenges that you have to address, because when you're high up in the sky, you actually, because of line of sight propagation from a lot of cells, you see a lot more cells than what you would normally see when you're on the ground. So that basically means you have more interference, and it's not only that what happens is, while the base stations are transmitting downwards to their terrestrial devices, the aerial environment observes that signal through the back lobes of the antenna pattern they're using to actually transmit to the terrestrial user. So that causes a lot of constructive and destructive interference in the air, and you see a high fluctuation in the signal you observe. So you have to kind of overcome that challenge, but applying this conditional random field framework to predict the best cell or the best two cells, we actually do get quite good results. So the figure is showing the cell prediction accuracy versus localization error. So if I'm not able to predict my position very accurately, then can I still preserve the accuracy of my prediction? And we are plotting two sets of results. The top are, with some more denser sampling grid of what I showed earlier, and the bottom sets are a little bit more sparse sampling grid. And we are plotting the results for best cell prediction as well as the best two cells, which are the top figures in this set of figures. So you can see that you can maintain fairly good accuracy, over 95% accuracy, even though you have large positioning errors in your system. So see, these results are sort of early results. They seem promising. And so if you note is that we've been able to exploit contextual information via machine learning in a very good way to solve the problem of aerial communication systems. More generally, we do believe, or we expect, that machine learning can be very useful in trying to exploit contextual information with respect to more complex systems like wireless autonomous systems, such as autonomous driving, industrial robotics, and so forth. So I'm going to actually give, Intel is doing quite a bit of work in this area. So I'm going to give a little bit of, even though we don't have results in this area, I'll give you some examples of how this could be useful. So actually, Intel has a whole science and technology center dedicated to this problem in collaboration with the University of Pennsylvania, where we are looking at context-aware networking for wireless, enabling wireless autonomous systems. And the center is focused on addressing the challenge of how do you support safety-critical autonomous applications over very unreliable wireless networks. And the key sort of focus of this center is rather than treating, basically you want to treat the wireless network as an autonomous system itself, which can learn and adapt to its changing environment autonomously. So then if you're trying to support an autonomous system over these autonomous networks, then what you want to do is co-design these two autonomous systems together rather than independently as it is done today. So the idea is that I want to take the autonomous system task and the wireless communication task together and design them together. And learning plays a key role in this center. We are using learning for different applications, just focusing on how do you learn this co-design approach, how do you improve wireless networking while learning, and also how do you learn over wireless? Like if I'm an autonomous system, how do I actually do learning over wireless? So it kind of opens up new opportunities to how you would exploit context in this system and how you use learning to exploit context. And you may not have thought about it, so I just wanted to give a couple of examples in this, on this topic. So if you take the problem of wireless resource allocation for controlling industrial autonomous systems, so say you have robots in a factory that you're trying to now control over wireless networks. This actually, if you're trying to move from a wired network to a wireless network, or at least the requirements come out to be very, very stringent for wireless communication. So people want very high reliability, 9 nines, and very low latency to actually support such applications. But what you observe is that most control systems perhaps do not require that type of reliable control. If they're already stable, they're not going to move from their stable point that quickly. So you can exploit this information to set up a co-design problem in terms of how you allocate scheduling, how do you do scheduling in wireless networks to take into account the state of the control system and the dynamics of the control system to actually save on some of your scheduling resources. So what happens is if you express this joint control and wireless resource allocation problem, you can show that the effective packet error rate or the data delivery rate that you need for controlling this, basically using the sensing information, actuation, and so forth, can be much higher without losing the stability of the control system. So what you want to do is basically schedule users that are very not close to the stable regions. They're basically in the unstable region and kind of service them more quickly than you would use the other users. And by using this co-design approach, we've done some initial results where we see that number of users to meet the control target, you can significantly improve the number of users by using this co-design approach. So the green is actually the co-design approach. The other two approaches are actually not using co-design, and you can actually increase. You can scale your system much better. And I guess we did not use machine learning for this set of results, but we've used a lot of heuristics to actually get to this result. So we do believe that machine learning can help us improve the performance of this system much further, and this is something that we are working on. So in this case, I actually gave an example of how a wireless system can use context from the autonomous system side to improve its performance. I wanted to give another example where an autonomous system actually can learn about the context of the wireless system. So here, I think this was mentioned, a robot is trying to plan its route or navigate autonomously in an unknown environment, and it does so by combining memory-augmented network through and reinforcement learning. And if multiple devices are trying to collaborate together, then basically they can collaborate while actually reading and writing to this external memory, which remembers where they had been, slightly sometimes ago. So while they're collaborating on this task of path planning, they are collaborating over wireless networks, so the learning should also take into account the context of the wireless network while they're optimizing this route. So while we don't have results, this is another area where we're trying to kind of factor in the wireless context into the learning problem. So I gave, I guess, just two examples. I think this is a pretty rich area for kind of applying machine learning, and we do hope to see more results in this area. So just to summarize, there is, of course, huge sort of surge to apply machine learning techniques to wireless applications. A lot of them were already talked about. We do think that context-aware design of wireless is an important application area. We showed some promising results. And we also think that this machine learning is a key enabling technology for wireless autonomous systems. And exploiting contextual information in this area, there are a number of examples that you can kind of use to improve performance. What we didn't talk about, but I alluded to in the beginning of the talk, was this area of emerging architectures, such as neuromorphic architectures, which can lead to very low power devices and can address dynamic workloads and learn on the fly. And so I think this is another area that maybe we can cover in a future presentation, but this is another area to watch out for in this case. So this concludes my talk. I think I'm ahead of time, so I did well.
Questions?
Nope.
I've got a question about contextual awareness. I think that this.
Okay,
this
because I think you had worked in this area before.
I'll come up there. Yeah, I wonder how broad do you think the concept is of contextual awareness? Does it extend to what end users want, or does it just extend to the environment?
I think it actually is probably one of the areas where you could really apply machine learning, because it's hard to predict humans. And if you can use learning to predict humans, then you can apply that in some clever way in optimizing the delivery of service or the connectivity service to them. So I think it's a pretty rich area for application here. I see some skepticism there, but yeah.
Thank you. Your results on self-search kind of confuse me a little bit. So maybe I can ask just a couple of questions there so I can kind of understand. What is the input you use for that self-search?
So you solve this graphical model. You have some truth labels.
What is the observation?
Yeah.
Maybe I can rephrase. What is the observation? In other words, what is the data you're putting into your
so
ML
okay, so for the known nodes, where the yellow nodes I showed you, you know the best cell, that node, you already have ground truth for those labels, and you also know the SINR conditions.
So you know all the SINR conditions of each
condition.
node?
Yeah, yeah.
So how do you obtain that SINR information?
I mean, some of this is that you've done, maybe, you've crowdsourced this information. There have been past measurements of this environment. Users or devices or aerial nodes have reported this measurements to this central entity which is trying to solve this problem.
Well, in your simulation, you show us a result there, right?
Yeah, yeah.
That show, what did you use in that result? That's what I'm asking you.
You use the SINR information and...
Well, yeah, but how did you obtain it in that simulation?
It's known. It's
so
not
it's
reported.
geneated?
Yeah, geneated, yes.
It's
In
geneated.
this particular case, yeah.
Okay.
Yeah.
So now, given that you have a geneated knowledge there, what you've shown is that you can, even though you have some errors, you can still maintain the cell search. My question to you is, but you did not show us that actually it's better. There are algorithms that are,
Fair, it's a very fair point.
You haven't shown us that, the ML is actually performing better. You just showed the ML error.
Yes. I agree that, these are very preliminary results, but it sort of shows that you could at least predict something, and more work needs to be done for sure. So we are not saying like this is the best approach you could use, but there is some promise in showing.
So let me ask the final question is, you have shown that ML has achieved something. Have you looked at the inverse part of the problem and say, what is the ML using to achieve this?
I mean, in some sense, yes. For this particular application that we showed, we think that this data can be made available because there is a lot of, for a drone example, you can actually do some prior measurements which do not need to be so dense. And in a sort of like a mobile network situation, you have a lot of crowdsourced data that you can use to get this information. So in some sense, there is, of course, use of that information, but that information may be available.
In other words, what I'm asking is very simply, if you have the RF fingerprint, why don't you use just a simple lookup table?
Yeah, there are other approaches of doing it, for sure. I mean, I don't think that we are saying that, this is the only approach you could use.
Okay, thanks very much.
Okay,
Let's
thanks.
thank the speaker again.
Thanks a lot.
Okay, so we're going to move on to the first panel of the summit. And this panel is going to be moderated by our very own WNCG director, Sanjay Shapatai. So I'll hand it off to him to let us know more about what the panel is about.
Thank you, Sujay. So the theme of this panel is that wireless networks are getting increasingly complex to design, operate, and manage. This is for a variety of reasons. There's increasing scale in terms of number of users and devices. There's also a huge diversity of the devices, and not just on the user side, but also on the infra side. The backhaul and the backbone network is getting more complex. And there's a diversity of use cases as well on how you exercise this network. So AI and ML have promised to solve all problems in the world. So we'll see whether it can solve problems in wireless as well, and that's what this panel is about. So we have 4 excellent speakers and researchers in this area. Dr. Arun Ghosh, Dr. Howard Huang, Vikram Chandrasekhar, and Konstantin Karmanos. I'll give more background about each of them as they step up to speak. We are going to, each of them are going to speak for 5 minutes, after which I have a set of questions, which we'll discuss back and forth, and then open up to the audience. So that's the format for this panel. So I'll invite Dr. Ghosh to come up. Arun Ghosh is the director of the wireless communications at AT&T Labs. He leads a team of researchers responsible for developing new technologies related to 5G, massive MIMO, backhauling for ultra-dense networks, and millimeter wave technologies. He graduated from IIT Kanpur and then his PhD from University of Illinois at Urbana-Champaign. Arun?
All right, thanks, Sanjay. So I have 5 minutes, and I'm going to be extremely respectful of that. All right, thank you. So, I guess, machine learning is a common thread to a lot of talks, a lot of conferences, a lot of workshops, and it's understandably so. It's a new tool that, we have recently started exploring, and, like everything, every new tool, you tend to sometimes overuse it. Sometimes you tend to abuse it, and I think that's okay. We need to understand where things like machine learning are useful, what their limits are, and you don't get a full picture till you really put it to the test. So as a network operator, what do we care about? There is certainly a lot of potential to things such as machine learning, and I think a common thread through a lot of the talks today has been that networks are getting very complicated. They're getting heterogeneous in nature. Macro cells, small cells, they're getting multiple radio access technologies, the licensed band, unlicensed band, all different kinds of. And how do I do slideshow? No, I think I'm trying to expand it to full view.
Present.
There you go. Thanks. So, one of the things that does, concern us, or in a sense that's something that we have to worry about, is the nice thing about traditional model-based systems has been that if you know the distribution of the input, it's very easy to predict the distribution of the output. So, an end-to-end communication system, or in fact a whole network, can in fact be predicted. At any point, you can predict the distribution of the output variable if you know the input variable, which is very nice because you can predict worst-case behaviors. And if you have to provide any kind of quality of service or guarantee any kind of reliability, then that comes in real handy, because if you know the input conditions, if you know the distribution of any of the parameters in between, you can really predict, what your overall system behavior is going to be. I think that is one thing, at least from a large set of problems. There are certain problems based on learning techniques that don't have that issue, but there are many cases, many examples of reinforcement techniques, learning techniques, where it's very hard to predict what your worst case will be by going through a certain amount of sample of data. And that level of inference is going to be very critical if you want to take some of these techniques and take them from where they are today and put them in real network. But I think that's one direction that we need to really think about. So from AT&T's point of view, there is a lot of role of machine learning techniques and even optimization of techniques, even for current networks. As we go into the next generation of technologies, there will be obviously other things that, we heard this talk by Professor O'Shea that, we can even bring signal processing in the domain of deep learning. But even without that, the current networks, there's a lot of role of deep learning or machine learning techniques for the network. And I think one point that, sticks out very strongly to us is about the network architecture. As I mentioned, the whole network has become significantly much more complicated. The devices, the kind of traffic that you support on the network has become extremely diverse, including the fact that, now we are operating multiple generations of technology across multiple spectrums, which have very different behavior going from millimeter wave to sub-6 gigahertz. So it's a optimization problem that has so many degrees of parameters, and sometimes we actually don't even understand what all those different parameters are and how they actually link to each other in something as large as a operational network. So one particular problem that we kind of like to work on, and I think there's an effort going on internally, and as well as I actually did see there were a couple of papers on this topic, is to really apply the concept of machine learning, especially for something like an integrated access and backhaul. So one of the problem that you face in an IAB network is to determine what your network topology should be, which essentially means which node needs to connect to which parent node, and including which UEs need to connect to which IAB access nodes. And if you have a network with maybe 2 or 3 or 4 hops, then you can see the sheer number of possible combinations is very large, and it's almost impossible to do an exhaustive search through all of them. And moreover, the topology may not be permanent. It may change based on changing load conditions. It may change based on one of the links getting blocked. It may actually change even based on mobility. So if the users move, if the nodes themselves move, then you have to really update the network topology. And I think this problem in general falls very nicely into the category of a Markov decision process. You have a certain state, which is the topology of the network, and once you have a certain action, such as a node getting blocked or a route getting overloaded, then you have a possibility of moving to a different state. And this is it may seem like a simple problem, but it could be very complex in terms of how you actually define it. Do you want to optimize for latency? Do you want to optimize for signal strength? Do you want to optimize for loading? So it is, and right now I don't have a clear answer, but this is definitely an interesting area. So for us, I think this is a critical area, and in general, network optimization, topology optimization, traffic optimization is something that that is a very vital field, that even current networks can utilize learning techniques to optimize. And that was really it. I hope I observed my 5 minutes. Thanks.
Thank you, Arun. Our next speaker is Dr. Howard Wine.
You want to use mine?
So I'm very pleased to introduce Dr. Howard Wang, who received his bachelor's from Rice University and his PhD from Princeton. He joined Bell Labs, and he's worked in various aspects of wireless cellular networks, including MIMO technologies, machine-type communications, and was elevated to a fellow of the IEEE in 2015. He's currently working on scalable technologies for precise localization.
Okay, thank you. Hello, everyone. Good morning. So I work as a researcher at Nokia Bell Labs, and I'd like to start by talking about the legacy of machine learning at Bell Labs. And so a lot of these areas that historically Bell Labs has contributed to were mentioned in Eric's talk earlier today. So starting with Shannon and his work on the mouse Theseus, moving through some of the first support vector machines in the early 90s, and then finally Jan LeCun's work on recognizing handwritten numbers in the mid-90s. So Bell Labs has had a rich heritage in machine learning, and as part of our heritage, we tend to not be so successful in monetizing these innovations, but hopefully we will do a little bit better this time. And so here I want to talk about this topic of machine learning and wireless networks. And so if we think about, say, the layers of a wireless network, we can start from the bottom with the physical layer, talk about the MAC layer, and talk about opportunities and challenges at each of these layers. Okay, so if we start at the physical layer, and we think about, say, a transmitter receiver and an RF signal is sent. This link is mostly pretty well known and characterized quite well with channel models. And in general, for problems where you have a well-characterized model, you can basically either come up with a good analytic or a solution or something based on simulations. I think in general, at the physical layer, because of the availability of these models, maybe the opportunity for machine learning might be a little bit limited, except when you start considering certain nonlinear effects like in the RF chains or sort of end-to-end effects that Tim talked about. And so, let's say the physical layer, there are some opportunities, but they might be somewhat relatively limited. If we move up the protocol stack to the MAC layer, we can think about problems of resource allocation in terms of space, time, frequency across multiple devices, say within a cell. Okay, so in a cellular communication network. And here, except for when you start with, say, a proportional fare scheduler where you might have some very clean analytic results about how to optimally do your scheduling. Beyond that, you might have to rely on some heuristics to come up with a good algorithm. But in general, let's say for a single cell, it's a relatively simple system, and so these heuristic algorithms you can do pretty well. So it might be a challenge for machine learning to do much better than what we've already discovered so far. If we go to a more complicated system, looking at scheduling across cells, and so this, I think, is where there's a much bigger opportunity for machine learning. So as the previous speakers have mentioned, because of the complexity of the system, especially when you think about the interaction of allocating resources across multiple cells and how shooting a beam in one cell is going to cause interference in an adjacent cell, and you have many different parameters that you have to try to optimize over. This is where I think there's a really big opportunity for machine learning. So I'd like to suggest a couple of opportunities here. One is the first bullet item there is in these complex systems, you might have to rely on reinforcement learning for doing your training, which means that you're running a system in real time, taking performance from, say, the device and sending it back to the network to do training to optimize your network weights. But if the system is so complex, then it might take a very long time for these weights to converge. So is there an opportunity to, say, come up with a faster way to train these networks using, say, a digital twin? So what this means is that it's analogous to what Google has done for training their robotic arm. So they have a robotic arm that they want to optimize the performance of, but they create a physical model and in simulations, train this ARM to optimize its performance. So is there an opportunity to create a digital twin of a wireless network by, say, modeling everything at a very low level, such as using ray tracing, using the position of location, using the location of users and devices to basically perform training of the system in simulations. I think there's also an opportunity for new measurements, like the previous speaker mentioned about using the location of devices to enable context-aware systems. And just as a final opportunity, if we think back at the physical layer, is there an opportunity for machine learning to actually come up with new technologies, such as localization or human sensing? So localization means finding the location of people or devices, using channel state information, and then for human sensing, this is the idea of using, say, Wi-Fi signals as a radar-type technique to detect the presence or actions of humans in a space. So these are just some high-level thoughts, and thank you very much.
So our next speaker is Dr. Vikram Chandrasekhar. Vikram is a Standards and Mobility Innovations. He's at the Standards and Mobility Innovations Lab at Samsung Research America. He received his BS from IIT, MS from Rice, and he's an alum from here. He's a PhD from UT Austin. His research interests are focused at the intersection between wireless communications, intelligent networks, and machine learning, and how to leverage these technologies to positively impact people's lives. He's been an active participant in various standards bodies, including 3GPP. Since 2009, he's been instrumental in key cellular standards, including 3GPP, LTE, new radio.
Thanks, everyone. I don't have any slides, but I'll just give you a dump of what I'm thinking of. So it's almost been 10 years since I graduated from here. And first of all, thanks to Sujay and Konstantin for organizing this, TWS. And in these 10 years, basically, when I was a student here, I was actually on the other side, presenting posters and stuff. And in the intervening years, I've not been here, but I've been actively following TWS. And finally, it's been nice to actually actively participate as a panelist. So thank you again. And by the way, this is the first time I've seen all 3 of my 5 PhD thesis committee members, Jeff, Robert, and Konstantin. I don't know where Gustavo is, but hopefully you guys don't give us a hard time now. So anyway, coming to AI and ML and wireless, I think at Samsung we are definitely looking very closely at various aspects of how to leverage AI and ML and wireless at various layers. I think there is actually, if I were to, the way I'm thinking of it is basically that there is a certain aspect of AI and ML which can be easily moved to what we are doing today in terms of managing a network or recovering if something has gone with the network. How do we use these AI and ML techniques to figure out what's gone wrong and to quickly enable the network to recover from it by applying the right corrective action? And I think there's a lot of scope for machine learning to play a big role there. So that's the first aspect. The second aspect is something closer to the radio access network side. Presumably at the MAC and PHY layer, one could think of resource allocation as an example, scheduling resource allocation. And actually, one could borrow ideas from some of the works done in parallel fields. For example, from MIT, there was a very nice work on Pensieve, which was a neural network-assisted reinforcement learning algorithm to basically improve the quality of streaming video through a neural network. And some of those ideas there can actually be leveraged in wireless communications to improve resource allocation. From a physical layer perspective, obviously we have seen great works. For example, O'Shea's work on autoencoders. I think in terms of, as we get closer to the shorter time scales, a lot more thought has to be given in terms of what it really means to apply machine learning for wireless. And I think more research has to be done, fundamental academic research probably, to get insight at what it means to take these ideas and take them to reality, right? Because a lot of people, people from 3GPP and the IEEE community have spent a lot of years optimizing these systems to where they are today. So, and these systems are operating so close to the Shannon capacity. So we need to really understand what it means to apply some of these ML ideas in a practical communication system. So at Samsung, we are looking at all sides of things, but I think there's a lot of potential overall. I kind of think that we are we are right now at a stage where we have some toy examples of how things work, but we are not yet there in terms of fundamentally understanding what it means to take ML and AI in these networks. And I think Arun had some good illuminating ideas on how we could, what are the good research directions to look at. So, but I look forward to a good panel discussion. Thank you.
Our next speaker in the panel is Dr. Konstantin Karmanis. Konstantin is a professor at UT and the incoming director of WNCG. He received his AB in math from Harvard and his MS and PhD from MIT. Joined UT in 2006 and now is a professor whose research interests on decision-making in large-scale complex systems, machine learning, and computation. Konstantin.
Thanks, Sanjay. So my two main areas of research are in optimization and machine learning. So I am happy and conflicted when I see some of the kind of work that's happening on the ML plus wireless side. So Arun mentioned that some things get forget your exact words, maybe overdone initially or overhyped. And I think that we may be in that kind of scenario right now, although I do also agree with what Arun said, that it's okay and it's exciting by itself. It's a proof of concept. So that's my ML side, being interested and excited to see how far we can find empirical success. On the optimization side, I can't help but be skeptical when we ignore structure, because one thing optimization has been very successful at is exploiting structure even when it only captures a small element of what is actually happening in reality. We're very good at solving optimization problems with lots of uncertainty, with missing or corrupted coefficients. And the way we do that is we think about, we don't run huge genetic algorithms. I certainly don't. But we use the kind of structure we know. So more specifically to one of the main questions that Sanjay has asked, how can ML and AI build better systems? I think one component which is really important, which I haven't heard too much of today, is the prediction in time component. We've heard a lot about how machine learning can be used to solve instantaneous problems of what do I need to do now? So what do I need to do to achieve a particular operating point? But especially as wireless systems improve, data rates grow, latencies decrease, what are we particularly concerned of? On the one hand, we could say not much, but that these will naturally take care of themselves. But I know that that's not true, because applications always catch up to create new bottlenecks. And one of the obvious bottlenecks that we're seeing is that both machine learning and wireless are increasingly going to play roles in critical infrastructure, where you can afford less and less to have any fault. So I think one of the great possibilities here is going to be in trying to predict when you're going to run into trouble. So I think that this aspect of prediction in time, it also actually links very well to Nageen's talk, is an important area, an important role that machine learning can take, predicting what's needed and predicting what operating points we want to be at, and also predicting how the environment will change and when that could provide challenges. I'll leave it at that and look forward to the rest of your questions.
So to get this conversation going, I put together a set of 7 questions and sent it a few days ahead to the panelists to think about. And we'll go through these questions and hear their various thoughts. And then I'll invite the audience to sort of give them a hard time. So let me start with question 1, which is, what are the problems, either new or long-standing in managed wireless networks? And why cannot the methods we have used for a long time, we have built a lot of experience in managing networks. Why is that not enough? Why do we need AI ML? Arun?
Maybe I can start with that. I think some of the current approaches really depend on being able to develop a model. But we know on things like user mobility, traffic, there can be certain degree of predictability, but there is often, it's very difficult to actually build a model around that. And the second problem is, as I said, things are getting, significantly large, complex, and Konstantin might actually disagree with me on this, that yeah, it is probably possible to optimize some of that. But I think machine learning provides you a simpler and perhaps a bit more undefined approach to come up to a solution. But again, the main thing one needs to understand is that these new techniques, you always need to benchmark. You'll need to benchmark against well-tested and time-proven techniques.
Yeah, sure. I'll say I think this question is phrased in a way that where you say, why cannot we solve these problems? But maybe another way to say it is, how can we do much better? And I think that I think it could allow us to incorporate much more unstructured information as features, and that's been one of the successes. In particular, for example, in image classification, you put in largely unstructured data, and you get something out. So I think we could take kind of a Google car approach, where Google car has mapped out every I don't know what resolution, but every aspect of its environment, where every fire hydrant is, where every sidewalk is, absolutely everything, and then that gives a tremendous advantage. Maybe we could incorporate that in wireless as well. We've talked about GPS, but maybe I could use exact information about where the buildings are around me, and maybe we can have massive testing and use exact information about what the environment is. So maybe there's novel possibilities.
So the way I would think of it is that, so today all the modern wireless networks provide you with all the tools, and the way they're implemented is, we have all the tools, but we use some simple heuristic or simple rules to make decision making. As a simple example is you're doing handover between cells. Today, probably one comes up with fixed handover thresholds or fixed handover decision rules, but the networks are not really optimized to organically, grow or shrink the coverage as a function of the traffic, the offered load in the cell, right? So AI and machine learning, on the other hand, thrive best under uncertainty, right? So when the decision making is blurry or the rules are not clear, that's where AI and ML their performance tends to shine. So, so there are certain approaches where time-tested approaches work, but they're not working as, we could do even better than those. Another way of looking at it is, for example, most traffic today is, from the point of view of the scheduler, for example, there have been a lot of hooks provided for doing QoS scheduling, but modern schedulers just do some simple treat all the packets with the same priority and apply some simple rules or do proportional fairness. But one could do much, much better if you apply some simple ideas from AI or ML to basically recognize what flow these packets belong to, and maybe the scheduler can then come up with better decision making, and because it learns to recognize what the user is doing without requiring feedback from the user. So basically there are a lot of, I think, possibilities in wireless networks where AI and ML can be used, not necessarily to change the whole block completely, but take parts of the blocks where there is uncertainty and exploit it rather than attempt to fight it.
Okay, so maybe I'll be sort of the ML skeptic in this group, and maybe I'd like to suggest, okay, I think a lot of the current time-tested approaches can solve a lot of these problems. A lot of things are very well known in terms of modeling, in terms of the effects of interference, but then there are these new dimensions that, say, Konstantin mentioned about taking advantage of location of buildings or location of the users. But then I would like to ask, okay, what is the marginal improvement of ML given that accounts for these complexities, and what is the complexity of the ML algorithms themselves? What is the cost of that improvement? And I think that's what I am very interested in people quantifying when we try out these new ML techniques.
Thank you. Just a follow-up question from this conversation. So you mentioned that a big power of ML methods could be that you could use unstructured representations. You just feed in raw pixels and it gives you answers. So that has happened a lot in neural nets because of the convolution layer and these architectures which have evolved. Is there what is the data we are trying to use in ML, and are there good ways to represent that, or some intuition that's clear in the community that can be used to sort of start these kinds of methods? Anyone?
No. I don't know. I think that's a good question. I think we barely think that we understand that convolution is the reason, even in an area that's been around for such a long time. So I think that's important. No, I think another question that we'll probably get to later on, but I think really relates to that is, what do we learn? What are we going to, let's reverse Tim's talk and say, can we learn from what the outcomes are? Now, in Tim's talk, we were recognizing the outputs from, these are things that we already knew to be good. But of course, we don't want to just replicate things we knew to be good. We want more complicated situations. So are we going to learn? And I'm sorry, maybe I'm just giving away the last question. Do we need to learn? That's the flip side of that.
So let me move to
I guess you get to ask things, not me, but.
See, I'm on the moderator side. I don't need to answer these questions. So let's move on to question 2. So suppose let's wear the hat of we are machine learning believers, in which case, how should wireless networks architectures evolve to allow full integration of ML methods, or is it already ready? Maybe I'll start the other way around.
Yeah, so maybe in answering this one, maybe I'm answering a later question also, but I think that there's a possibility of integrating additional sensor information that's used to optimize the ML network. And so an example that was talked about earlier is the use of localization, so the location of each device. So if each device can send back to the network its estimated location along with, say, the quality of its channel, I think this type of information would be very useful in training ML networks. And this would basically eliminate the need for mobile drive testing, which is how networks are typically optimized today, where you have a van that is sent up by the service provider that drives through the neighborhood and measures performance as a function of location. So there seems to be a good opportunity there for using additional sensor data to improve these networks.
Thank you. I'm actually a bit of a skeptic when answering these kind of questions because one today does not even know what it means to apply AR/ML to, even some simple toy example, leave alone the whole wireless network architecture. But let me take an attempt at it. I think along the lines of what Howard said, I think I would answer it in 2 parts. The first part is adding additional hooks in the architectures to basically get KPIs or some kind of counters to know how exactly is the ML algorithm performing, right? Because in the end, if for some reason a certain part of the network doesn't work, for example, the call drop KPIs become bad, one needs to know which part of the ML pipeline is not working and what is the reason why it's not working. So the architecture should evolve to provide the right hooks and interfaces to allow the operator or the vendor to pinpoint the problem where it is occurring rather than treating it like a black box. That's the first aspect. The second aspect is the decision making that the ML module does should be explainable. In other words, a human operator should be in the end figure out what's going wrong and step in if needed. So there needs to be a very clean and modular way to explain the decision making of what it does and come up with heuristics to replace it if that part is not working. So it has to be some kind of a plug and play kind of architecture, I think.
Yeah, I'm happy with those.
Yeah, I think it is a very similar thoughts to what Howard and Vikram said, but I would particularly focus on the part of the network that's between the handset and the network, which is essentially your the wireless link part of the network. All ML algorithms, by inherent nature, require a lot of information, require a lot of data. And today, there is very little data that comes over that. Of course, there is very little sensory data, but apart from sensory data, you also require data pertaining to the characteristics of the link. I mean, physical layer parameters. Today, there's really nothing coming in. So unless you have that coming in, where does that, how do you operate that, the ML engine? And which then leads to a very interesting question is that if I'm going to really consume so much bandwidth, sending that data, I mean, have I eaten up the benefit that I, created in the first place?
Absolutely. I mean, yeah, it's getting back to feedback and how are you best using a channel, yes. So that brings me to the immediate following question, that if you are going to deploy ML first, where would you do that? What are the pain points in the network where you can immediately show the bang for the buck? So I'll come back to Arun.
I think a lot of it has to do with not so much of the it has more to do with some of the architecture and the planning today. And these are I would say problems on the simpler side. Today we choose network optimization. We pretty much pick a single parameter and we just stick with that for the whole network, because it is simply a very difficult task to really go to every place and optimize that. If that whole process can be automated, I think it's the automation aspect of it, that really helps. If some of that can be automated through some of these learning techniques, then I think that's an immediate, that's a very self-contained, immediate, pain point that perhaps all networks, wireless and wireline networks, can take advantage of.
I think possibly fault diagnosis could be something that could be potentially implemented without even thinking about new sensors. So I'm not talking about a setting where, just using the wireless environment to detect, to understand better why things aren't working. So that could possibly be something.
Yeah, definitely agree with both Arun's and Konstantin's root cause analysis, fault diagnosis, then basically optimizing, rather than fixed thresholds. Actually, I've seen some good work coming from MWNCG as well. I read Professor Brian Evans's work on partially blind handovers between sub-6 and millimeter wave. So things where you can apply machine learning to improve, handovers. I think actually I'm more, I like question 3 better because there actually, there are tons of places where in the wireless network where you can identify, the key point is to pinpoint what is the problem you're trying to solve and where in the network does it reside. I'm actually more optimistic about it.
So I think getting back to the proposal of having more feedback from devices about the quality of the communication link at a given location, I think that is an important consideration. If each device is feeding back its KPIs all the time, it might be too much in terms of the uplink data rate. But then what if there's a new class of devices, say a drone or an autonomous robot that is constantly wandering through your network, and that is dedicated to taking measurements of your wireless system. Just a thought of a new class of devices that could be used to enable your ML network.
So the next question is about how much should autonomy run in such a network. What I mean by full autonomy is at all time scales. So should we move to full autonomy where they completely manage all operations? At the fastest time scale, we have started seeing some of these kinds of issues. Timoshe's talk was fantastic in this space. Physical layer parameters, receive the decoding is what I mean by autonomy at very fast time scales. But then you could deal with it at a next scale. How should user association be managed? How should spectrum association be managed? And at the highest level, you could ask whether machine learning algorithms even deal with MVNOs and decide policy on who gets to use what bandwidth. And then there is no network operating room, essentially, which I'm sure AT&T is worried about all the time. Instead, you just let a machine learning algorithm run the whole thing with very, very slow human interface, meaning maybe once a day. That's the level of human interaction. So is this a good view? Is this a good approach? Should we even go there? I'll open, since instead of going ping pong, I'll let anybody who wants to address this first.
I can take a stab without going into the particular very doom and gloom example that you took, but more about timescales. So anytime you have a new tool, a whole new concept, particularly a solution where predicting the worst case behavior is difficult, challenging, and maybe in some cases impossible, I would say it's best to start at long time scales. And the main reason is that if you do see something go wrong, you actually have other ways to mitigate that, intervene. If you do things at very short time scales, you really don't have any other ways to intervene. So I think, for all of us, when we start putting this in the real world, there needs to be a backup.
Yeah, I'm sure that our robot overlords will find the right answer to this question. I think I'm curious where the overhead's going to go to kind of all of these ideas that we're proposing, and there's going to be some additional burden to incorporating different aspects of these solutions. And is it going, because in some way these are collective, like what I said before about the much more precise information about the wireless environment stemming from the physical environment. Is this now going to be something in the header that all packets that are sent, so that at the base station you build up this information as it changes, or where exactly is that burden going to fall? So I think that's an interesting and I guess perhaps unrelated question.
Yeah, so actually on the feedback and the information part, I actually think what we have today already is quite considerable. I mean, all you have to do is take a look at the NR specification, look at the amount of parameters that is present. I think from a physical and MAC layer point of view, absolutely no, the information is already available at the base station. Today, base stations just do some simple some rules, but they don't really use information and percolate them to the higher layer. So yes, so that would be one change that would be needed for facilitating these ML algorithms. So I would tend to think that you want to start at the slower timescales for implementing, but actually even before going down that route, I think one needs to be precise about what it means in terms of interoperability, right? So today, most modern networks, you have not just one vendor who deploys these, you have a bunch of people. So if something goes wrong, who's to blame? Is it a certain point of the network blames? Does vendor A take the blame, or is it vendor B? Or how is the fault shared, or how is the fault resolved? Who takes responsibility? So these kind of simple questions first, one needs to come up with a better understanding, So that's more, not technical, but actually more of a procedural aspect. The second is basically coming back, is one needs to clearly know how to explain the decision making and infer what it is doing while making these decisions. That is equally important, as actually probably more important than the performance of these algorithms compared to, say, some known heuristic. That can always be done, I think. That's actually the easy part to me.
Yeah, I'll pass on this one.
So there are some interesting things which are arising already. What are overheads, who's paying for it, what are representations, and where is the data? We'll come back to some of these things after I'm done with these questions. I'll skip the sensing since it's been addressed multiple times. And let's get to this. So suppose you have machine learning algorithms which are running networks and making resource allocation decisions. There's a lot of discussion in many other communities right now about explainability, that somehow humans need to understand the decisions that need to be made. In the context of managing and running wireless networks, does explainability even matter, or do you even care about why decisions are made as long as you see the performance, whatever the performance metrics you care about? This is a really hot button item in much of ML. Is this even of interest in this community?
I would think so. You know, if things are, or even trends are impossible to explain from your intuition, it's very difficult to accept a result. So yeah, I think certain degree of being able to explain the results is required, because that then if you do understand why, or if you do understand the reasoning, then you can actually start to understand under what condition, under what similar conditions it may actually make a similar decision. And I think that is a very critical point, which I think goes back to your initial question, is that because of the deep convolution and of the multiple hidden layers, I think some structure needs to come out of there so that we can create some kind of an intuition based on that.
I'm skeptical about this because our starting point is that wireless networks are getting so complicated that we have to abandon models that we understand. And now we're coming back and saying that explainability requires us to provide some sort of simple explanation about what's happening. And I wonder if we're doing this somewhere else. So for example, if I'm designing a new aircraft wing, yeah, roughly we remember the experiments we did in 5th grade where the blow dryer blows on the wing, and because of like Bernoulli or whatever that's called, it goes up. But really what happens is we put this thing in a wind tunnel, I guess. This is an area I don't know about. I like speculating about things I'm clueless about, which is why Sanjay put me on this panel. So, really what happens is you put things in a wind tunnel and you take some measurements and you, I guess, try to solve some differential equations, which themselves you discretize, and is that explainable? I wonder. I don't know. Is that explainable beyond that first, if I propose a modification to an aircraft wing? So if we're doing the same thing now at very, it's not that we don't know anything about machine learning. About wireless. We know a lot about it, and now we're saying that, okay, but in a very complicated environment, we need to use some machine learning. I don't know how much explainability we can really hope for. I think, now I'm reversing myself, I think the danger of saying no is that we don't know what the performance is in cases outside of the ones that we've seen. That's the fear. So the fear is that I checked it on 100,000, 100 million, whatever data points, and it did great on those, but what about outside? Whereas if it's a physics-based model,
I certainly hope this never happens. I always hope there'll be some kind of explainability. I think, most of the work till today, we have built rigorous human intuition and understanding, and that's what is the cornerstone of today's modern communication systems, right? And I hope it continues to be the case. I mean, and particularly for like mission critical applications where, you know, you've trained the system with 1 million data points, and, you know, you got on a great blur curve, or you got on a great delay or throughput, and then you put it in a model with that model has never seen before, and things fall apart and you have no idea what it's doing, right? It's just like, you know, you have an autonomous car which is going around a curve or on a cliff, and it has never seen what it means to fall off the cliff.
So I like this question, so I'm just, if I can interrupt and ask you again, what does explainable mean? Explainable to whom? Does it need to be explainable to me? Do I need to understand it? Does my grandma need to understand it?
It should fall within the baseline intuition of the domain expertise.
But the person who is the machine learning expert and programmed this thing and intimately feels every aspect, every neuron firing and non-firing might say, this makes sense. But I can't tell you beyond that what...
Maybe the analogy is, say, taking an exam at school here, right? So if I have the capability to take an exam and get an A on it, but I don't really, okay, that's sufficient maybe, but I think it would be much more beneficial in the long term if I understood the underlying principles of what I'm being tested in that exam, so that then I could apply that intuition to later problems. And so it's about, I think, explainability is important for humans to then have insights about what to do in the next step, or how to improve or augment these ML systems in the future.
We can go on forever on this, but let me go to the next question and then circle back to the audience, because I want to give some time for all of you to talk with the panel. The last question is, what does success mean for ML? Are there when would you say that it's actually better? Based on some test data set? Is it public? Is it shared? Is AT&T going to internally decide that it's successful or not, and Verizon does the same thing themselves? Or is there something beyond that? Is there a community understanding of success? And since I brought up AT&T, I'll give it back to Arun.
I was kind of hoping you would start from the other end, but I knew that was not happening. Yeah, this is obviously a tough one. I think this is even tougher than your previous, because, you know, one would, you know, traditionally today what we are doing is we are operating or using ML for, in many cases, not always, but in many cases we're using ML for a lot of problems that we already know how to solve, which is a good thing, at least from a point of view that it allows you to see how it performs compared to some of the time-tested methods. So one could say that, you know, in that case, if you do better than that, then you can show. If you do better than a model-based approach, you know, you would say that's a successful. But it becomes a lot harder to judge what success is when you start operating or using ML for a lot of things that have really never existed in the past. And, you know, consider, you know, network automation, for example. You know, you have some kind of a, you know, AI agent that optimizes various aspects of your network, you know, and it runs real time. That has never been done before. We don't actually have a benchmark based on, you know, other methods to actually judge. So I think judging success is going to be certainly subjective. I think one part that might be interesting is that if we start adopting ML for large-scale network optimization, period, I think that would, you know, be a success. But, you know, a lot of places, a lot of things need to fall in place. You know, guarantees, being able to support testability. How do you test this thing? How do you actually interoperate between two different nodes, as Vikram brought out? You know, can the two ends of a neural net reside across two different nodes? Say that's. So many questions still to be addressed. So I'm not sure if I'm giving an answer to this, but it's certainly time for me to pass it on to maybe Konstantin.
Yeah, I think that for big service providers, this is a difficult question. But I think if we draw a parallel to what's happened in say computer vision, and many areas like voice recognition, image classification, no one had to wait for this explanation to come about. it's just been implemented. Various parts of the industry have run away with it, and I don't think this is going to happen overnight with AT&T. It can't. There's too many obligations, and it's just too big. But we could see success, meaning successful products that are implementing it and just selling well. You can't stop me from buying something to put, to put in my house if it's better than the previous product. And if that has the same runaway effect that we've seen, I mean, we've seen massive, like, complete displacement of previous state of the art. So it could start from a smaller scale.
Yeah, I'll keep my answer to a very simple things, because this question is quite, one could abstract it and consider any number of things. But at a very fundamental level, I would consider two things. The first is, how well does it do compared to the state-of-the-art algorithm or heuristic, and what are the complexity considerations. The second level is, how well does it generalize? So I've trained it on a certain model, and how well does it generalize when I expose it to something unknown or unfamiliar to it? I would start with these two, and then one could always add other considerations. Yeah.
Very well said. So yeah, I agree with you.
So there are many things that have come up here: overhead, representations. But I will stop talking, and I will invite the audience to ask the panelists questions. I'll just walk around.
Hi. Yeah. So can anyone precisely define what is ML algorithms here, which you've been completely using throughout the panel, define? And a second, like a follow-up question is like, do these sort of consideration bring about new, let's say, mathematical questions which are not being considered by people doing traditional statistical machine learning?
Yeah. Do you have a microphone up there? We do. Okay.
Yeah, go for it. You have to press that. Okay.
Yeah, maybe I'll maybe try to answer sort of a related question, which is what are the opportunities for machine learning for something, say, outside of the traditional realm of communications? And so I think I touched upon this in my initial remarks. So I think, and then it sort of relates to this question 7 also. What does success mean? It means that machine learning can enable something that we hadn't able to achieve previously, or does something much better. So there are opportunities, I think, for machine learning in areas like, say, Tim mentioned in RF sensing, and these technologies for human sensing and localization. So how do we use information that's already there in the communication channel, like channel state information, and use that using machine learning to learn something about something else in the system. So I think that's a really exciting opportunity, I think, for ML.
So I think some of the challenges we have with ML is that you can do great with a nice little training set, but then if things are too far away from the training set, then you don't know what's going to happen. And that's for critical systems, I think, for critical infrastructure, that's a big problem. Another new one that I think we haven't addressed here at all is what is the right, we have this, the simple car is autonomous car, what should happen if if the certain scenario that wasn't known before, how should it handle it? And it turns out, this recent publication just this last 2 weeks is pointing out how these actually, what you should be doing actually is ethics that varies from country to country. So it's so cultural. And this can also be for mission critical systems in the wireless space. And I don't think we've even thought about that. What if you put this infrastructure in a new country where actually there's other criteria that you'd even think of? So I wanted to challenge you with that one.
Yeah, I think machine learning is not unlike people learning. I mean, you need to be exposed to situations where you make ethical decisions, and therefore get rewarded one way or the other if you make the right decision over time or not. So I mean, I don't know if anything can be not exposed to something where it doesn't know the cost of making a decision one way or the other, and then be asked to make a decision and always make the right decision. So a lot of these things which have ethical implications, we definitely need to train it, along, and especially this may actually fall in the case where you have to reinforce it, based on an award, based on the decisions that it makes, because its decisions are not self-contained. It impacts others.
Yeah, I think that's a great question, and it gets back to how do we evaluate? Because if we can evaluate on a test set, but you're only evaluating with respect to some performance metric, and if you don't have models or you don't have some kind of explainability, then if I ask you how well does it do on a different performance metric, which might be, you're talking about different ethical considerations, different fairness considerations, or different demands for critical infrastructure, et cetera, we probably have no clue in that setting. So I think that's a really good point, and actually clarifies some definitions that we might go back and put on what should we ask for explainability. Yeah, thank you.
Thanks, Sanjay. Jeff last year told me I spent too much time talking before I actually asked the question, so I'm going to be a little bit briefer this year. So in one sense, I find this, let's see if we can liven up this panel a little bit. I found your answer to question 2 distinctly unsatisfying, because you guys never answer anything about the architecture. So I'm going to rephrase Sanjay's question to be even more pointed. So do you agree in 3GPP, where they only created the a function for AI, the AI function, is that the right architecture? If not, what should be the right architecture?
Yeah, I don't think you want to define a function in 3GPP. 3GPP never defines algorithms or what happens inside of a box. What you do want to define is what kind of data and decision-making capabilities you want to exchange between nodes to aid them for making a decision. I mean, in 3GPP, we define interfaces. We don't define how things work within a box.
You're right in that we don't define what's in the box, but in SA, you know in SA, they define the AI function, right? There is a new function created in the release for the AI function, which is to deal with AI. The question becomes, is that the right architecture to create a single new functional entity?
Probably not.
If you don't think that's right, what should be the right architecture?
I think that's a great question, and it really depends on what you want that AI function to do. If we want it to do some kind of a balancing of traffic, balancing of load, balancing of scheduling decision, it's definitely not SA-based AI function, right? It needs to reside somewhere inside, and I think we already have a function that does that. Except it's not based on learning techniques, it's based on heuristics or simulated techniques. In order to aid any kind of ML-based solutions, we just need to define what that exchange of information and the exchange of data needs to be, and define some kind of behavior that we expect out of it.
You're right, Arun, you're exactly right on that. So now, given that the exchange of data is the most important, right? Do you expect a single function to work, or do we need multiple functions? And where does this function sit? That's the architectural question, right?
I have no idea. I doubt it will be a single function. I really doubt. But it might be, depending on what you want it to do, it might be multiple functions. I actually don't have a very good idea of what that AI function in SA is for, what its roles are. But I really doubt if it's in function, if its job is to do any kind of optimization at the MAC or PHY. I seriously doubt that.
So I guess my comment would be, and maybe this is because of sort of a naive understanding of the of how the system would work, but you could implement the AI system without any standards changes, right? Everything could be done over the top, where any feedback of performance from a UE back to the network could be just done in an over-the-top fashion. You don't need standardization for the feedback. You don't need standardization for the AI function. Okay, but then you could standardize it, and that might improve some efficiencies for, say, a control plane version of this system. But then the question is, okay, what is the marginal benefit of that compared to some over-the-top implementation of an AI system?
Thank you. Actually, I completely agree with Howard. So traditionally, 3GPP just provides the tools and the interfaces, and how we do things is left to implementation, and that's good because it encourages ingenuity and innovation. And the context of AI, I think we all, how we do things in 3GPP is we start with what is there today and evaluate, incrementally, okay, if do we really have, without going to the specifics of the SA's AI function, we need to first evaluate what is out there today with the tools we have currently. How can we use them? And then is there any marginal benefit to adding new functionality or introducing new network entities, right? So one has to provide it through rigorous technical evaluations, and that's the way to go. And at present, I think nobody really has an idea what it means to have an AI function. So we start with being skeptics, and then convince us it works, and then we can move on from there.
Okay, I guess my question is, so for explainability and generalization, are we trying to apply a higher standard now to machine learning systems than we ever did to, previous systems? And is it unreasonable? So, like, if we look at how we designed systems before, we might have trained on and tested in AWGN and Rayleigh channels and cost models, or 3GPP channel models, but then we also expected to generalize to every condition in the world, right? And is ML any different, really? Because it's kind of the same generalization question. And then secondly, ML provides a whole new set of tools for analysis. You've got like feature maps and class activation maps and adversarial examples, and a lot of ways that you can address explainability in entirely new ways, which is just, it's a very different tool set than what we've done in the past. And then, it's back to really what degree of explainability do we want? It's hard to explain things in the context of complex data sets and complex channel models. But, the tests that we've done in the past are really like, Burr curves and testing under various channel models and various well-defined test conditions. And we can really do all those same things with these sorts of models too. So why do we expect some really, crazy high standard now?
Yeah, I think maybe I can take a stab at that. I think conventionally, right? What do we do for heuristics, right? They all come out of rigorous mathematical analysis. We come up with bounds, and we have an understanding of where they work and where they don't, right? And we also have good radio network simulators to test them out. So there is a well-defined methodology. Actually, one of the things with these AI-based systems also is that once you train it, how do you integrate them into the radio network simulator and try them out? So there are very practical issues involved in actually identifying what are the limits to which they perform and where they don't perform. So I think the whole methodology where one trains them and one tests their performance in live networks is still I think people are figuring out as we speak. So I think because it's such a new concept, one needs to be a bit more careful about how we introduce them.
And one last question. I think I want the community to go back to the basics. I think people talk a lot about all these algorithm advancements. So the key question for all these advancements is ImageNet. So where is the ImageNet for wireless communications, right? So that's number one. Number two, it seems like all these techniques are mature that you can actually apply out of the box is going to work, which is not the case. Like RL, for example, is not working most of the time, right? And people apply to robotics, and for locomotion tasks, it's not beating even like PID controllers. So I'm just saying two questions, like where's the ImageNet for wireless communications? Are these algorithms actually ready for application, right?
to wireless communication?
Yeah, so the first question, where is the wireless ImageNet? So I think that the wireless problem is very specific to location and topology and environment. And I don't believe there is an analogous ImageNet for wireless communications, because you basically want to have your system work in any type of environment. And so, so ImageNet would be, say, for a standardized set of inputs and outputs, but that would be only for a specific environment. So I don't think that you can necessarily generalize that for the wireless case.
Okay. So let me also take a shot at that, since I'm a moderator and that will close. It's not even clear what ImageNet means, because when you transmit, you're changing nature. And so what the SNR regime changes if some other base station is transmitting. So what is, it's not even clear what is a fixed data set, because the data is good, this is, state is going to adapt depending on what strategy you're going to use. So it's a fun conversation, but maybe we can continue that over lunch. And so that brings me to the end of this panel. Let's thank the speakers and the panelists. And I'll hand back to Sujay.